Hey, Physics 30, how's it going? We are going to talk about atomic physics today, our last and final unit slash chapters. Um, I've decided not to split this up into two chapters. It's going to be one test at the end of week 12 there. So we've got a few things. So sorry about my face was kind of glitching out there. So this last little unit here is just more, it's going to be more or less, the first part of this first week is going to be more or less history of the development of the current model of the atom. We won't talk necessarily about with the quantum probability field model of the atom. We're going to probably stop near the Bohr model, which kind of explains a lot of the stuff that we see throughout history or throughout observations that we can observe, right? So we're going to go through this, and it's going to start off pretty history heavy, right? Then it's going to move into some more science-based and math-based stuff, right? How do they discover what they discovered? So we're going to go through four main models, right? We're going to go to the Dalton model, the J.J. Thompson's model, Rutherford's model, the Bohr model, and then the last model there is going to be the quantum model. Well, there's going to be no questions, or I'm not going to test you on the quantum model. It just exists as far as we know. But we'll talk about who helped develop that quantum model. How do we know it kind of exists a little bit near the end there? But yeah, so let's just delve right into it. So we're going to talk about the first guy. We're going to talk about Dalton. Okay, Dalton. He was the first modern scientist to make contribution to atomic theory. Before this, they were the Greeks, and they thought things were made up the elements: earth, wind, fire, heart, if you want to think Captain Planet. But Dalton was the first of the modern scientists, and he needed to change the model of the atom to model, of course, the things that he saw happening within his chemistry lab, right? So his theory is basically just from the idea that chemistry, how models, through chemical reactions, mass was conserved, atoms shifted around from one place to another. I'm going to sneeze here. Okay, I was going to sneeze. Okay. So just basically just on conservation of mass from chemistry, he came up with this idea of that molecules of just matter and stuff are just consist of these atoms, these little indestructible particles. And he called them atoms, right? That was the first thing. I really glitched with my face there. He didn't really know too much. He just thought they were indestructible. All atoms of the given element are the same. So he did recognize that gold atoms are different than copper atoms. They had different weights to them, different sizes, right? Each element's atomic mass is characteristic for that element. So you notice that gold always had the same atomic mass, no matter what kind of gold you had. We'll talk about isotopes later on in the next week here. But the majority of if you have gold, you know how much it's going to weigh. If you have copper, you know how much it's going to weigh. Atoms combine together to create molecules and compounds and stuff. So he knew that. And he knew that atoms can either be created or destroyed, but they were just rearranged inside these chemical reactions. Okay, that was Dalton. He created these indestructible, he didn't really create it. He just created a model that atoms are these indestructible particles. So this brings up his first the model, which we call the billiard ball model, happened in 1803. So these are the things down here. You can see that his model helped explain chemistry pretty much. It helped explain the conservation of matter, the law of definite proportions, and the law of multiple proportions. Those are just like stoichiometry from chemistry. How do we explain that? How do we explain that we get 2 of oxygen versus 1 of hydrogen, or vice versa when we separate water into its constituent pieces? So that's all about stoichiometry. So he had to develop this model. Hello. All right, sorry about that. So Dalton's model, the billiard ball model, just helps explain just chemistry. All right, it's a pretty easy thing. Just a billiard ball, just something that's indestructible. It can't be pulled apart into smaller pieces. So at this point, they don't know what's inside the atom. They don't know about protons, neutrons, or even electrons, right? They know about charged particles, but they don't know how they're charged or what constitutes a charged particle at this point. Okay. Later on, using what we call a cathode ray tube, J.J. Thompson comes along here. Now, J.J. Thompson, pretty famous guy. He has a pretty sophisticated little setup. Obviously, a cathode ray tube here that shoots out this beam of charged particles. He knew they were charged because they bend within magnetic fields and they're affected by parallel plates. So he knew they were charged particles. He didn't know specifically what those particles were, right? So he was just playing around with these charged particles, these negatively charged particles that are coming out of the cathode of his tube. Now, you think a cathode, because of chemistry and stuff, cathode would be the positive piece. It's only positive because it's losing the negative pieces. It's losing negative electrons. So it becomes positively charged. So it's just called the cathode because the cations would move towards it, okay? Because it was positive ions would be attracted towards this negative electron. Okay? So many scientists use these cathode ray tubes. They were an interesting little device, and I'll just scroll down here to the picture of this little device here. So here's this typical cathode ray tube. In the 80s, 90s, and the early 2000s and stuff, these are really popular because they were just the basis of tube TVs, those big, chunky tube TVs or computer screens that you might still have sitting around your garage and stuff. No, it's not part of these LCD screens anymore. But they would just control these beams using magnetic fields and electric fields towards a screen on the other side over here. So the screen on the right side. So electrons would get burned off through this cathode here. So they would just heat this up or pass electricity through it. So electrons would burn off here. They would shoot off in all directions here. But they weren't electrons. They didn't know electrons yet. We know they're electrons now, but he didn't know that. So they shoot off in all directions. Some of the electrons will pass through this little piece right here. So this is just a parallel plate system that's going to speed these electrons up. So they're going to pass through this little system, right? So some of the electrons go through there, but they're all varying speeds. They're all different speeds because they come off this thing at different speeds. The ones that happen to go straight through are all going at different speeds as well. But they will accelerate through this little system. You get faster and faster because you got a positive plate. So you would have a positive plate is on this side. And then you would have negative plate on this side. All right, so they would accelerate through. When they get to the other side, they're going pretty fast. And then they go through this other parallel plate system right here, where you might have a positive plate on the top or something, or a negative plate on the bottom, or vice versa. And the electrons would bend up and hit the screen detector on the other side. All right, that was the basis of his of any cathode ray tube experiment. Okay. So, like I was just saying, okay, cathode rays are essentially just glass tubes, evacuated gas under very low pressure. High voltage is applied across the tube, and it produces electrical discharge. Okay, so they boil off these charged particles. Now, what they noticed about these charged particles is that they always travel in straight lines. To them, it travels in straight lines. If you give it a little bit more time, the electrons' gravity would pull them down, but they were going pretty fast. So they just seemed like they were traveling in a pretty straight line, but gravity would eventually take hold. Might be considered moving particles, right? They were deflected by magnetic electric fields, so they thought they were particles, right? Just a big beam that was coming through. It doesn't matter actually what the cathode was made of. The properties were always the same. So this came to help us come to a conclusion that if I use gold cathode or copper cathode, aluminum cathode, or any type of metal cathode, I always seem to get the same beam cathode ray that comes out of these things. So it helped us draw this conclusion that all types of metals, and later on all types of atoms, would have something common within them. Right? Whatever this ray is made of is inside of these atoms, and all of them would be the same. They would all have the same similar pieces inside them. Okay, so we come down here. Let's go to. So in his experiment, he did a few different things. He had a 3-piece cathode ray tube, and what you saw in that picture, there's only 2 pieces in that picture, but he added a 3rd piece to help him develop and prove certain things. So in his experiment, depending on the properties of the cathodes, were deflected by electric and magnetic fields. Okay, so he knew they were charged. In his first part of the experiment, all right, was to see how far the beam would bend passing through specific magnetic fields. The electrons were accelerated through a potential difference. Right? The electron gun, in the electron gun part of the cathode tube right here, this part here, it gets accelerated between these 2 plates right in here. Okay, it gets accelerated. That stream of electrons is then passed through a magnetic field, which bends them. Then he has a detection device at the end, so he can determine the radius of curvature of the bend. So he knew that as charged particles enter into a magnetic field, they would move in a circular motion. So he'd know how much they curved based on where it hit his detection device. His goal was to find what he called the charge to mass ratio of these unknown elements. Because the 2 things that he didn't know the charge of these elements, he didn't know the mass of these elements. So he just wanted to find kind of the combination. And he kind of theorized that every element would have their own charge to mass ratio. So he wanted to kind of show that all of these cathodes produce the same element with the same charge to mass ratio, so you can come to a conclusion that they're all the same particle. So every atom or every metal would consist of this particle that they're trying to find. Okay, so let's go back here. Let's just discuss the pieces of this. And so in step 1, he accelerated his charged particles. Okay, so I'm going to pull up my formula sheet if I can find it. Okay, a bunch of papers here. I'm just going to pull up my formula sheet here. My face is all messed up there. Okay, good. Okay, so we're going to accelerate a charged particle, and my formula sheet is different than yours. I'm going to find out where it is now. We're going to use this formula right here. So it's kind of hard to see. I'm going to change my voltage. The energy of the charged particle is going to accelerate based on the charge. But the thing is, I don't know what the charge of this particle is. But that's fine. Right? We're just going to accelerate through that using the charged particles. Okay, so essentially this is what he did. We might come back to this formula later on. All right, and then I'm just going to rearrange this. Problem is we don't know the Q, so we're just going to ignore that for now. But that's his essential process to accelerate this. Okay. And then those electrons, like I said before, they get accelerated and they all have different speeds as you go through here. So all those electrons are going different speeds through this magnetic field system now, and they bend. Okay. So these electrons are all coming through. Let's just draw one over here. A bunch of electrons. Well, sorry, charged particles. We don't know the electrons yet. So all these negatively charged particles in the beam are traveling, let's say this direction from left to right, into this magnetic field that he's producing here. Okay, so he produces this magnetic field. So this is the magnetic field. They're traveling fast enough now, so they're not going to get trapped in the magnetic field. They're going to be able to get through to the other side. So this electron will hit this magnetic field. I'm going to use my left hand here. I'm going to put my fingers into the page. Okay, my thumb is going one direction. My palm is going down, according to my left hand. Right, into the page, forces downwards. So it's going to experience a force downwards, and it's going to curve. And by the time it gets here, it's going to be going a different direction now. Okay, and then over on this side over here, he would have a detector. And he would be able to detect an electron hit this area. Maybe you see a flash of light at this point because you just have some kind of fluorescent material that would react with those charged particles. Okay, but all these particles are traveling at different speeds. Okay, so some are going faster than others, so some will bend in here instead. Some are going slower than others and actually might be hit the bottom of this collector and not even hit the detector, right? So we got all these different charges, or sorry, all these different speeds, which causes different radiuses of deflection. Okay, but he was able to determine them, so that's good. Okay. So let's just focus on one of them. So he detected one of them. Okay, so let's say he detected this one here. Okay, he knows the radius of curvature. What he's going to do now is going to use his information that he knows is that when a charged particle enters into a field, which one is that one? That was that one in the middle here, right? When a charged particle enters a magnetic field, it's going to experience a force, in this case, a magnetic force. And as it changes direction, that magnetic force also changes direction, just a little bit more each time. But all of these are pointing towards the center of something, right? So he knows that this is going to produce some kind of circular pattern. So we can say that the Fm, the magnetic force that they experience, is equal to the Fc, the centripetal force. Right? Remember, that's like an F net. And all F nets are m times a as well. Okay? Cool. So he also knows this formula, QVB. I'm not going to worry about, well, I put vectors in here, but we're just worried about the absolute value. Everything's perpendicular here. Circular motion has been around for a while, so he knows some of the formulas like QVB, or sorry, mv squared over r. That's just the acceleration formula. He knows the magnetic field. He's producing this magnetic field, so he can actually determine what the strength of that is. So he's going to rearrange this. And the thing is, he doesn't know too much about this. He doesn't know the mass or the mass of the charge. So he's just going to rearrange it to get those two things on one side of the equation. The charge to mass ratio, charge to mass, so Q over M. So Q divided by M. All right, so he divided the M to the other side, which just happened to be Q over M, and then he just divided everything else to the other side of this equation. It's got V squared over R, there's another V, and there's a B. So this V will cancel out with one of those. So he can determine the charge to mass ratio this way, okay? If you knew the speed of the electron, you could divide it by the radius of curvature, which you can measure just based on this detector here. So knowing where it hit the detector, he knows the curvature, the radius of curvature, sorry. And he knows the magnetic field strength because he's producing this magnetic field, either using permanent magnets or electromagnets at this point. The problem is he doesn't know the speed of the electron, okay? So let's go through the two parts that we've done so far. So he's accelerated electrons. So they're all going lots of different speeds, but they're going really fast, so that's good. So they go in a straight line. And then he passes those electrons through a magnetic field, and they bend in a circular pattern. And using that, he should be able to find the charge to mass ratio if he knows the speed of the electron, or sorry, the charged particle. I keep saying electron. He knows it. We know it's going to be electron later. Sorry. Okay. So he needed to figure out a way to find out this velocity, right? And this is where he's famous for. Sorry, this video is getting a little bit longer. Yeah, so I'm going to just do the last part. Okay. And then we'll go into the math in the next video. So he set up a different piece. So if I go back up my picture up here, he set up a piece between the magnetic field and the accelerator that he has here. So he added a piece right in here. That was what we would call a velocity selector. He put something here that would allow him to select which velocities he'd want based on just change some knobs and stuff, and you'd be able to get different speeds, right? And it would effectively just get rid of the other velocities and allow them to slam in the plate and just leave the system altogether. So we got to figure out how he did that. So let's go down here. So he set up a system like this, where he had parallel plates, positive and negative charges on top and bottom, and he has a magnetic system on either side of this. Okay? So he wanted to know what would happen if electrons entered into this system. So this is like a cutout view. So this would be in the system, it'd be more this way. The electrons would fly in this direction, and the magnetic field would be here. So that's where the magnetic field would be. This would be the side view. Okay. So the electrons would fly into here. Based on what we know, they would get deflected downwards. He knew they were negatively charged, so he put in the top here, he put positive charges on the top plate that would pull them back up. So we'd try to stop them from being deflected, right? Deflected downwards based on the knowledge that this would experience a force down, which is the magnetic force. So to counteract it, you would have to have a force upwards, in this case, the electric force. Okay? So you'd have these two forces. If they balance each other out, the electron would travel through undeflected. So there would be electrons going through undeflected. Right? But wouldn't they all get undeflected? Right? There would be a force up, there would be a force down. So wouldn't they all be undeflected? So all the electrons would just go through no matter what speed they are? I don't know. Okay. So just to complete this diagram here, I'm just going to put the electron here. I know it says into the screen, so it should say out of the screen. Okay. So I'm going to have an electron coming out of the screen here. We got a magnetic field going this direction from north to south. So this is my magnetic field. So this is going to experience, based on my hand rule, my fingers are going to go in the direction of the magnetic field. If I were to do it this way, my thumb is coming out of the screen. My hand would be going downwards here. So I would experience a force downwards. Nice little magnetic force. And because these are negatively charged, they would be coming upwards. So that's just the front view. Front view or back view? Yeah, say this is called this. Okay. So they're going to go undeflected. So what we need to know is that we have these two forces. These two forces, to be undeflected, they must be the same. Okay, so to be the same, let's see. So FE has to be equal to FM. Okay, so over on the FE side, that's just dependent on the electric field and the charge of the particle. Okay, so the FE for all the electrons would be the same. All the charged particles would be the same because the electric field is the same. Remember, no matter where they are in the field or the parallel plate system, the electric field is always the same. The charge of the particles is always the same. So the FE is always the same. Okay, so they all get the same force upwards. But on the other side here, the magnetic force is dependent on the charge, which is always the same. Okay, that's good. It's dependent on the magnetic field, which is the same as well. It's a nice constant thing that he created. But it also depends on the speed of the electron. Or sorry, the charged particle. Right? It depended on that. So the faster they were going, the more magnetic force, the more force downwards. So the faster they were going, they would get force downwards because it maybe that wouldn't balance out the electric force because they're going too fast. So if they're going too fast, they go down. If they go too slow, if they go too slow, their magnetic force decreases, and then the electric force pulls them up. So the only way to get through undeflected is to be just the perfect speed. Now, one more problem about this formula here involves the charge. And what we know, what he doesn't know the charge of the electrons yet. Millikan hasn't come along here and said, here's the charge. Use the charge and help us solve this question. Doesn't know that. But it's a pretty smart mathematical mind, and hopefully you guys determined it as well. There's a charge on each side of the equation that I could just reduce this out. So it doesn't actually matter what the charge is. There's a question later on. I thought I had a question later on. Does it matter if the charge is positive, negative, or 2 coulombs or 1 coulomb or something? It does matter if it's positive or negative, because if it's positive, it deflects downwards. That's a different story. But it doesn't really matter what the size of the charge was. It would just cancel out. So he rearranged this equation here. For V, solve for V, that's what he wanted. He wanted to know how fast these ones that are going undeflected. This one, how fast is that one going? The ones going too fast go down, the ones going too slow go up. This one here is just right. Goes right undeflected, and then goes into the next part of the experiment. So all he needs to do, if I just rearrange this, is take the electric field and divide it by the magnetic field. And that's it. Actually, just these should always be absolute valued. Direction doesn't really matter in this situation. So to find out the speed that is going undeflected, you just take the electric field and divide it by the magnetic field. Okay, so this helped them actually determine the charge to mass ratio of these particles, and that's what we're going to do in this next question in the next video. Oh, this has been a long video. I'll see you in the next one.